All right, for today's video, we're going to combine a lot of what we've been talking about so far this unit into a process what we call predicting products. So now that we understand how to balance a reaction and the 5 categories of chemical reactions, we have enough information for us to figure out how a reaction is going to proceed just based on the information of the reactants. So we're going to go through all 5 types of reactions, and we're going to start here with the first one, combination or synthesis. And again, we've got our generic A plus B yields one compound product. And then we've got some steps here that'll go through the process of what we're going to be doing. So for a synthesis reaction, we're going to look at the metal and the nonmetal and the charges that they typically form when they become ions, and then creating that as one balanced product. So we're going to combine the cation and anion using the appropriate ratios based on their charges. Because right now we've got aluminum and oxygen as elements, and they have a charge of 0. But when aluminum and oxygen combines together, aluminum as a +3 ion and oxygen as a -2 ion combines together to form Al2O3. And actually, I already made a little mistake here because the last step of this whole process is to balance the reaction, and I didn't leave myself any room to write a coefficient. So again, we've got Al2O3, and we've seen this reaction before, but we know that every element in this reaction isn't balanced. We've got 1 aluminum, 2 oxygen, 3 oxygen, and we want to start by balancing the oxygens first, because this has to be a coefficient to get us some kind of a multiple between 2 oxygens and 3 oxygens. But I wanted to show you what it would look like if you started with the other element, which we could do. Like if we put a 2 here, we've got 2 aluminums. Technically that's balanced. But no matter what, we're still going to have to balance out the oxygens. So there's always going to have to be a 3 and a 2 there. And if we run into this process, all we have to do is kind of default back to say, well, is there any element that still is now not balanced? So we need to just always go back and do a double check to say, like, well, now I've got 4 aluminums, so then this 2 actually needs to be corrected to a 4. And then again, we go back and say we got 4 aluminum, 6 oxygen, 6 oxygen. So now we've got a balanced chemical equation. All right, so there's no harm in starting with one element over the other. It's just sometimes you might go back and have to correct a previous step. Okay, so we've got a couple examples here for each type of reaction. I'd ask that you pause the video after you create the product of this chemical reaction down here, the second example, and then we'll go through the process of balancing it. So again, if we've got elemental sodium and elemental chlorine, these have both a charge of 0, but when they combine together, they're going to form a compound between sodium and chlorine, but sodium is a +1 ion and chlorine is a -1 ion, so that formula is just going to be NaCl. We got to kind of fight the urge to create a product that already has a balanced set within it. We can't just slap those two things together and say NaCl2, right? So if we've got 2 chlorines going in, we need a 2 here to have 2 chlorines coming out. And then if we have 2 sodiums coming out, we need 2 sodium atoms going in. So 2Na, 2Cl make 2 NaCl. Okay. If we talk about decomposition, again, this is the breaking down of one reactant into many multiple products. And so what we're going to do is really just write the metal and nonmetal as elemental products, checking to see if any of the elements are diatomic, and then balance. So if we look at this first reactant, we've got silver 1 oxide, or just silver oxide, and the elements that it's going to break down and produce are silver and oxygen, remembering that oxygen is a diatomic element. So that's actually going to break down and form Ag plus O2. Again, the kind of urge there is to just split them apart and just make it Ag2 plus O and call it a day because the reaction's automatically balanced. But the way that these elements are going to form when they're on their own is Ag is going to be singular by itself, and oxygen is going to find another oxygen atom and pair it up to form that diatomic element. So now when we go through imbalance, we've got one oxygen somehow forming two oxygens, so we're going to have to double up the number of oxygen atoms going in, and that means 4 silver atoms are going in, so 4 silver atoms are going to have to come out or be produced. Right? For this second example, this is kind of a unique instance, and this is what we call carbonate reaction. Anytime we have carbonate or bicarbonate as a compound, as a decomposition, one of the common products that's going to be produced is CO2. So we've got like a carbon and 2 oxygens bonded in here, and then what's going to be left over is a magnesium bonding with oxygen. And since magnesium is +1 and oxygen is -2, that's going to form MgO. Right? And oops, I get in the habit of giving myself some blanks. We're going to say blank MgO plus blank CO2. Now, if we do a quick kind of mental atom inventory, we can see that we've got 1 magnesium, 1 carbon, and 1, 2, 3 oxygen. So this is actually a completely balanced out chemical reaction. So it's all ones. So for a carbonate or a bicarbonate reaction, we want to pull a CO2 and form that into the product, and then the remaining elemental components will be the other product here. And this is one instance where we've got a decomposition that forms 2 compounds instead of 2 elemental products. Next up, we're going to talk about single replacement. And for single replacement, we have to really look at what is the type of element that's by itself. Remember, for single replacement, it's an element plus a compound, and then it's going to replace one of the 2 ions in that compound and make it by itself. And what gets replaced really depends on the element, whether or not this A is a metal or a nonmetal. So we're going to replace the element in the reactant compound. Metals replace metals, nonmetals replace nonmetals. Determine the formula of the product, and then we need to double check if the product element is diatomic, if this B by itself is going to be diatomic. There's a couple of things we really need to take into account. So if we look at this first example, we've got Na plus FeCl2, classic single replacement element plus a compound. Sodium is a metal, so it's going to replace the iron in this iron 2 chloride. So the first element that's going to form is just Fe by itself, and it's not a diatomic element, so we don't have to put Fe2. And then the product that's going to form is what happens when this sodium ion is now bonding with these chlorine ions. Well, sodium is a +1 and chlorine is a -1, so the formula of this product is going to be NaCl, 1 sodium and 1 chlorine. Again, we really have to make sure that these product compounds are formed correctly based on their charges, and then we go back and balance out the reaction. So if we have 2 chlorines going in, we need 2 chlorines coming out. And then if we have 2 sodiums being produced, we need 2 sodium atoms to react with that 1 iron 2 chloride. Okay, for the second example, again, if you want to pause the video and practice, see if you understand this pattern logic here, see if you get the product formulas correct, and then we'll go through and balance it. All right, so the first thing we want to look at is the fact that the element here, sulfur, is a nonmetal. So it's going to replace the nonmetal in this potassium fluoride compound, which is fluorine. So that fluorine is actually going to be the element that gets replaced or kicked out. But we also have to remember that fluorine is one of the 7 diatomic elements, so we're going to make that F2. And then the compound, the other compound that gets produced in a single replacement reaction, is now going to be potassium reacting with a negative sulfur ion. And if potassium is a +1 and sulfur is a -2, then this is actually going to form the compound K2S. right? So again, this is 2 plus 1 potassiums, 1 minus 2 sulfur, and then it's F2 because fluorine was that diatomic element. So we can see here that if we have 2 Ks and 2 Fs, then that means that on the reactant side, we need 2 Kf, or 2 potassium fluorides, to react with just 1 sulfur to form those two products. All right, we've got 2 more types of reactions that we're going to practice. Double replacement. Again, we've got the kind of shorthand notation here. This one I think is actually kind of the easiest because you have to do a little bit of legwork with the reactant side to figure out what the charge is, and then you're just switching the 2 positive components. Right? So if we look here, we've got calcium sulfide reacting with potassium fluoride. Classic double replacement. Again, we identify it as double replacement because it's 2 compounds reacting together. And so calcium here is acting as a +2, sulfur is a -2, potassium is a +1, and fluorine is a -1. So the positive potassium is now going to react with a negative sulfur. So it wants to switch what it's bonded with. So the first product that we could form is K2S. Again, because we have 2 +1s for that 1 -2 that it's now bonded with. And then the other product is going to be the other positive ion bonding with the other negative ion, calcium fluoride. But because calcium is a +2, we need 2 -1 fluorines. So if we have 2 Ks and 2 Fs, to balance this reaction, all we need is to put a 2 in front of that potassium fluoride reactant. Okay? So here's one more example for double replacement. Identify your charges, pause the video, practice writing out the products, and then we'll come back and balance it. All right, so again, we've got sodium +1, chlorine -1. This time we've got aluminum +3 and oxygen -2. If we take the time to figure out those 4 charges, the products are actually pretty straightforward because now we've got a +3 aluminum bonding with a -1 chlorine. So the first product is going to be AlCl3. Again, we got the +3 aluminum and 3 -1 chlorines. And the other product is going to be the other positive ion, sodium, bonding with that -2 oxygen ion. And that's going to form the product Na2O. 2 +1s for 1 -2. So this one's a little bit tricky to balance because our aluminums are off. We got 2 aluminum in, 1 aluminum out. Our chlorines are off. We've got 1 chlorine in, 3 chlorine out. Sodium's off, and oxygen's off. So this is really where that ping pong method that I referred to in the other video really comes into play. Pick one element, balance it on the product side, and then take that one element that it's bonded to and go back and keep working it back and forth until you get a balanced chemical equation. So really we can start with any one. We've got 1 sodium here and 2 on the product side. Let's go and balance out the sodiums by putting a 2 there. Okay, we've now got 2 sodium, but now we've got 2 chlorine, 3 chlorine. So the chlorines aren't going to balance easily because this is always going to be in a multiple of 2, and that's always going to be in a multiple of 3. So we need to change this coefficient so that our chlorine count can get to a total of about 6. Right? So we're going to adjust this chlorine and make it to a multiple of 6. And we're going to adjust this chlorine with a coefficient of 2 to give it a multiple of 6. Again, this one, because it's AlCl3, can only be in counts of 3. So this could be 3 chlorines or 6 chlorines, or if this was a 3, 9 chlorines. So 3, 6, 9, 12. This number here can be any number we want because it's 1 chlorine by itself. But we also have to keep it an even number because we always have an even number of sodiums on the product side. This one's a little bit tricky to kind of figure out that balance. Once we figured out that 6,2 chlorine count, we can go back to the sodium and say if I've got 6 sodiums going in, I'm going to need 6 sodiums coming out. So I'm going to make this a 3, and that gives me 3 oxygen atoms, which balances out those 3 oxygen, 6 sodium for those 6 sodium, 6 chlorine, and then 2 aluminum for those 2 aluminum. So a little tricky, but definitely possible. This is another good example of sometimes you get a really difficult equation to balance, but you just kind of have to go back and keep changing the numbers to see what eventually will work as long as the formula of your products are written correctly. All right, the last type of reaction that we're going to practice the products for is a combustion reaction. And from the last video where we talked about this particular pattern, this was the in bold, all caps, always, combustion reactions whenever you have carbon, hydrogen, and oxygen always produce carbon dioxide and water. So there's really no predicting the products. There's remembering that for this type of a system, the products are always carbon dioxide and water. Okay, now we've seen this one before. This is kind of a common combustion reaction. We've got 3 carbons going in, so we need 3 carbons coming out. We've got 8 hydrogens going in, so we need 4 water to give us 8 hydrogens being produced. And then the trick here again is to always get your oxygen count on the product side counted up correctly. We've got 3 CO2s for a total of 6 oxygen atoms. We've got 4 water molecules for a total of 4, so a grand total of 10. So this is where we're going to put a 5 in front of the O2 reactant. All right, the next one's a little bit more challenging, so I'd ask you to pause the video, try this out, and see if you get the coefficients to balance on your own, and then play the video to see if you did it correctly. All right, so we're going to start by balancing carbon and hydrogen. We've got 2 carbons here, so we're going to put a 2 to get 2 carbons being produced. We've got 6 hydrogens here, so we need to get a total of 6 hydrogens on the product side, and we're going to do that by putting a 3 in front of the H2O. Now, if we pay attention, the total oxygen count, if we've got 2 CO2s, there's 4 oxygen atoms here, 3 oxygen atoms here. So if we add them together, this is a total of 7. And this can only be presented in even numbers. So there's 2 ways that we can balance this out. One of them is to say that there is a number that when we multiply it by that subscript to 2, that it equals 7. And that's to say that we've got 7 halves, or 7 over 2. Because 7 over 2 times 2 is equal to 7. And then that gives us the total oxygen count. The only thing is that we always have to have this in the lowest whole number ratio, so we can't leave a fraction in this balanced equation. So if we get this situation where we do 7 halves, what we would have to do is multiply this whole system by 2 to get that 2 out of the denominator. The other way to go about this, anytime we have an odd number of oxygens on the product side, is to say that if I doubled this number and I doubled this number, I wouldn't have 7 oxygens, I'd have 14, and then 14 is an even number, and I can get 14 oxygens on the reactant side. So the way to double these coefficients is to double this reactant. So if I put a 2 here, I now have 4 carbons going in, so I'm going to need 4 carbon dioxides being produced. I have 12 hydrogens going in, so I'm going to need 6 water molecules being produced. And now with the 4 CO2s, I've got 8 oxygen atoms, plus these 6 oxygen atoms for a total of 14. And 14 is a multiple of 2, which means I would need 7 O2 molecules to balance that reaction.